With a neighborhood function, what we are doing is having a kernel, in this case a three grid cell by three grid cell kernel, acting on every grid cell in the input grid, which is shown on the right here, on the four grids on the right. And then this kernel moves along, sometimes it's called a moving window, so that that black point would occupy each of the grid cells in the grid except for the very edges where we just can't fit the kernel. And what's happening here is that we're using the central grid cell, represented by the grid cell, the gray grid cell with a point in it, and all of its neighboring grid cells, in this case any grid cell that shares an edge or a corner with the central grid cell, in order to reevaluate the value of that grid cell that has the point in it. And then this kernel just moves along until each of the grid cells in the original grid has been reevaluated and given a new value. So just to kind of talk about what some of these neighborhood functions might be, we can take the mean of that kernel, and in this image here in the middle, we see what the original values are, and then we see what the recalculated value is for the one central grid cell in this case. This is before the window starts moving. We're just looking at the kernel sitting on top of one grid cell neighborhood at this time. The mean would be adding those 9 values in the grid cell, 1 plus 2 plus 3 plus 3 plus 6 plus 3 plus 3 plus 9 plus 3, and then dividing by 9 to get a value of 3.7. The median is if we list all of those numbers in the grid cells in order, 1, 2, 3, 3, 3, 3, 3, 6, 9, and take the one that falls in the middle of that list, the 5th position, we would get a value of 3. The minimum is obviously 1. The range varies from 1 to 9, so we get a range of 8 in this kernel, and the maximum has a value of 9. We'll talk about slope and aspect in a different lecture, but majority would be the value that occurs the most often, and in this example, that's 3. So one way that we can use a neighborhood function is to kind of clean up our data a little. In this example here, we're looking at data that has been classified into maybe a remote sensing image that's been classified into roads, corn, beans, or others. And if we look at the image on the left, there are some areas where we kind of get these pixels right in the middle of what otherwise would appear to be, for example, a large field of beans. We just kind of get a little bit of pixelation in there of other things. There could be little patches of corn in there, but it seems pretty unlikely that's what it is. And in this example here, it's been cleaned up. So how does this kernel work? Well, this is called a majority filter, and in this case we're looking at a central value and we're seeing what that central value is. In the example at the top there, we're looking at one where the grid cell in the center is corn, but all 4 of the grid cells it shares an edge with have been assigned to beans. So in this case, the majority filter would say because the 4 neighboring pixels, the 4 neighboring grid cells are beans, we're going to reassign that central pixel to beans because that's what we think it's most likely to be. However, this doesn't change everywhere. If we only have, and in the example on the bottom, we can see that there is no majority. It's a 50-50 split. 2 are beans and 2 are corn, so we're not going to reassign that pixel. And so this just kind of looks at what the majority are and then decides whether or not to reassign or not reassign based on that majority. And once again, this would be used as a moving window, reevaluating every single pixel in this grid, in the input grid, to produce the output grid. One sort of thing that we can do with a kernel like this and using a moving window to move around our grid is to apply neighborhood functions that serve as low-pass filters. And in this case, we're using a mean. We're just going to, you can think of adding all those numbers together and dividing by 9 once, or dividing each number by 9 and adding them together. You'll get the same value. But in this case here, we're just running this mean filter over our data. And what we can see, if we compare the output grid cell values with the input, the highs get a little lower and the lows tend to get a little higher. So essentially what we're doing is we're smoothing out our data. We're getting rid of things that are higher value or much lower value compared to other things within the neighborhood, and assigning it a slightly different value because we're considering its neighbors, not just the grid cell itself. So sometimes we would call this a low-pass filter, and we would use a low-pass filter if we wanted to smooth out our data. For example, if we had a digital elevation model that we wanted to make look smoother, we could run a low-pass filter just to smooth out some of the bumps in our elevation data. Thinking of it the other way, sometimes we want to really enhance those differences or those bumps or those lines where things change. And we can also use a neighborhood function to do that, and we would call this a high-pass filter. And this type of high-pass filter shown here is specifically useful for edge detection. So if we look at the input layer on the top there, we can see by the shades of gray where the edges actually are. The left half of the grid has values, all the grid cells have values of 980. The upper right, all the grid cells have values of 940. And the lower right, all the grid cells have values of 900. What we're going to do is, if we're looking for differences moving from left to right or horizontal differences, we're going to use that high-pass filter, that edge detection filter, which is shown on the left. And we can see what's happening there. It has a 1 on one side and a -1 on the other side, so that when we add those things together, we're going to detect where those edges is, because the grid cells on the left are going to have a different value than the grid cells on the right. And the output from that would show that 980 minus 940 gives us 40, 980 minus 900 gives us 80. So all the values along that vertical strip in output A have values of either 40 or 80. If we look at the example on the right, where we're looking for a vertical difference, so we're looking for a difference as we're moving from the top to bottom of our page, we use that sort of kernel where we have, once again, a value of 1 and -1. It's not going to detect that edge that was detected in output A at all, because it's just not seeing that difference. It's actually only seeing it in 2 of the grid cells. But what we are seeing is that edge between the upper right and the lower right, where we have some values of 940 and some values of 900. Because it's completely consistent along there, a difference of 40 between those 2 grid cells, all of the grid cells in output B are going to have a value of 40. Another thing that we can use a high-pass filter for is noise detection. And noise is randomly distributed throughout our data, very different than the last example we just showed, but it tends to have values that are very dissimilar than the surrounding values. So in this example here, you can see that the kernel that's being used has a high positive value in the center, and then values of -1 for all of the neighboring grid cells. And then we're just going to add those all together and divide by 9 in order to get the output. So we can see in the first example there that that had a central grid value of 963. Once we do this operation, then we would get out a value of 35. What we can see is that if we do this to all the grid cells once again, as the moving window moves across the grid, in the output layer, our highest points that are shown in black in the top layer tend to stay black in the lower layer, and our lowest values that are white in the top layer become even more low, negative, in the bottom layer there. So we're really highlighting where we think the noise is by either highlighting where the very high or very low values is by using this high-pass filter that is designed to detect noise.